Hello, everyone. Welcome to Twitter Seattle. Some of you probably did not know we had an office here, let alone that we did run our media platform team here. So I run the media platform team up here in Seattle. We're responsible for all the back-end media processing for native Twitter media. So if you tweet an image or a video, it's going through services on the back end that are run by the team based up here in Seattle. So it's a pretty important part of the Twitter infrastructure. We're processing very high volume of images, especially high volume of images, but as you can imagine, most of our effort is focused on the video space right now. There's a lot of excitement. We did a lot of work last year on the NFL Thursday Night Football, and we have a live product that we're running in addition to our huge VOD video business. Promoted video and video advertising makes up more than 50% of all Twitter revenue. So we're a big part of the overall Twitter business in addition to just part of the product that's very noticeable. We had to make a last-minute change to our talk topic, so I apologize to those who are excited to hear about ad insertion for the NFL. I know Gabe sent mail about that. I won't get into the details of IP and the video space, but anyway, we still have hopefully a very interesting talk that John put together. John has been engineer here for 3 years at Twitter?
Yeah, almost
3 years. He's a staff engineer on my team. He's been involved in pretty much every big project we've done with Twitter Video, including the launch of Twitter Video. And now, most recently, has been working a lot on the live video and ad insertion products. So he's going to give it a video now of our VOD solution. So here you go, John.
Thank you, Josh. Hi, everyone. Josh did a quick intro, so I'm going to skip the introducing myself part and kind of jump into the topic. I'll talk about our video on-demand processing platform and some of the design decisions we made. Here's an outline of what I'll be talking about. I'll start with the kind of the requirements and what the business landscape was like when we launched the first version of video processing, native video on Twitter, which was a little over 2 years ago. And then I'll dive into the design, how we kind of tackle those requirements. And here's an outline of kind of the design aspects. So I'll start with first what native libraries we decided to integrate with and how we integrate with them. And then how we decided to handle ingestion of the file from the user's devices, and then what kind of pre-processing we needed to do to make sure it's actually a video that can be tweeted. And then finally, to how did we design a system that transcoded all the different variants for supporting different platforms and different bandwidth situations. Then I'll jump to, we launched the V1 about 2 years ago, and then the landscape kind of changed and some of the requirements evolved. So I'll talk about what those, the most important changes were that we had to accommodate, and then how we went about accommodating them. Looking at the landscape when we were first launching the video tweeting capability, some of the most important requirements were around brevity and being real time. So brevity, Twitter's DNA is to be short and concise. Edit your tweet maybe multiple times before you can actually send it out, so that you get the message across and it's brief. And to kind of comply with that theme, we decided to land on a 30-second limit, which actually in certain ways made our life easy because we didn't have to worry about long videos from the start for a V1. And the other important thing was to make sure that we don't stand in the way of the user and them getting that information out to the world. So for instance, when if someone with 10 million followers tweets something out, it's critical for the fan out to happen as quickly as possible so everyone knows what's happening immediately. And likewise, video processing is expensive, it can take a lot of time, but we needed an architecture where we kind of minimize that time so that we can say, yes, this video is really a video, and we think we'll be able to transcode it, so let's go ahead and let you create a tweet and get start fanning out that tweet so people start seeing this information. And we needed to support the major platforms that the Twitter app runs on. So that was our iOS app, Android app, and then web. So this implied we had to support different video formats essentially. So for iOS, for the V1, we were doing HLS. And then for web, we were doing both MP4 and WebM for Firefox. And for Android, we were going to do MP4 first with a plan to transition to Dash quickly so that we can do adaptive streaming there as well. And obviously, the solution needed to fit within the existing kind of Twitter software stack. We didn't want to kind of reinvent the wheel and run on DCs other than Twitter's DCs, so that we can leverage all the know-how of how to write good distributed systems. And that also meant the language-wise. So Twitter is a Scala shop heavily on the back end, and it's got its own libraries such as Finagle that makes async server-to-server communication very seamless and easy. So we wanted to reuse that as much as possible, and we wanted to kind of shift our business logic, even for video processing itself, to that Scala layer as much as possible. And finally, video processing is expensive. It's very CPU bound. It uses a lot of storage. So we wanted to do whatever we can so that we minimize the costs of running the backend. Now I'll kind of discuss what native libraries we chose to use and then how we chose to integrate with those native libraries. In terms of, and I don't have as much knowledge here, so forgive me if I kind of get something wrong, but we were essentially trying to decide between LSmash and FFmpeg, and for the most part we decided to go with LSmash because it's got richer features for being able to deal with MP4 containers. And one thing I didn't mention is for V1, we were planning on only accepting MP4s for uploads. You could argue a downside of LSmash was that it didn't have a command line, client, so process forking was really not an option for LSmash anyway. But we also wanted to do, instead of process forking, we wanted to do native library calls, within a process, because we wanted to be able to, from the native code, we wanted to be able to get the frames of the video back to the Scala layer, so we can do most of our business logic, like manipulation. Let's say you want to rotate the frame, scale it, whatever. We wanted to be able to do those in Scala because we didn't have as many people proficient on the unmanaged stack, but we had a lot of strong engineers that can do stuff in Scala, so we wanted to expose the capabilities to more people that are already familiar with the Twitter backend. So that implied, and our services are Scala, which is based on JVM. We needed to go through JNI, and how we go through JNI, we had a bunch of options. So the simplest one would have been to have it in the same JVM where our service is running, accepting requests from other servers in the Twitter backend. And so this would have been, maintainability would have been good. We were able to write our Scala code, and we were not incurring any latency of forking a process or anything like that. But there was a huge downside, which is security. So imagine, I'm not even talking about someone trying to inject an attack vector, but just a bad video that causes the unmanaged code to crash. Well, that would bring down the entire JVM for the service, and now your service isn't responding to requests from other services within Twitter. It has to be assigned to another host. Your availability goes down. And this would have been made worse by the fact that clients were probably going to retry on that because they see a failure, they don't know what this is, so something must have gone wrong, let me try again. So imagine the client trying this video 5 times and bringing down 5 instances. So that was a no-go. So we decided it has to be in a separate JVM, and a simple way of achieving that would be every time you're trying to run one of these primitives, you just launch a separate JVM and kind of do it there. The problem with that is we go back to the latency issue, and actually it's worse now compared to just forking a simple process. The startup of a JVM has several seconds of latency, though this was also a non-starter. So we landed with our final approach was to go with a separate JVM server. So essentially in the same host we have the Scala service that's talking to all the other Twitter services, and then we have a pool of other JVM processes that are only accepting requests via local sockets to actually kind of run the job and return structured data through a inter-process pipe. So this had all the good aspects we wanted. It had the security, because if one of these crash, well, it's, that's sandboxed. And what we did was, let's say you want to have a maximum concurrence of 5 of these things doing stuff. You could have a pool of 8. So if one of them comes down, you plug in the other one, and you bring up the other one in the background without incurring any latency for actual requests that are making it to your service. And the downside was that this was the most expensive implementation, but we chose to go with this. It added a few weeks to our schedule, but I think in the end it was worth it. Now I'm going to discuss how we get the file from someone's device to our data center, and then what are the things we do to make sure, yes, I'm going to let you tweet this out. I give you a media ID and let you tweet that out and let others see it and try to play the video. For uploads, we are using what's called segmented resumable uploads, and the timing worked perfect on this one. We were actually just about to do this, we were doing this for photos, so we were able to use it for videos. So even with photos, what we experienced was that without, so if the user tries to upload the entire image in a single HTTP call, try to maintain a TCP connection, in markets such as Brazil, on a mobile connection, that's literally impossible. The failure rate is too high, so they can never reliably get the whole file across. So what we do with segmented resumable uploads is we have actually separate HTTP requests for uploading individual parts of the file, and then they upload chunk 1 through n, and then they say finalize. So then we kind of concatenate all those pieces together, actually commit the file, and start the pre-processing. So once this is done, once the file is there and they call finalize, this is it for my file. Now we need to make sure that this video is something we're going to be able to transcode and play on all the different devices, all the different formats. And our validation consisted of demuxing the video and then decoding every frame. The assumption was that encoding is somewhat deterministic once you have decoded frames. So if you're able to decode them, then we should be able to encode them reliably. And we did some additional pre-processing on the file so that come transcode time, we can do things a little more quickly. And so what we did was to kind of chunk up the file. So we identified the existing GOP boundaries in the file and saved each GOP as a separate file with its own header. So then the idea was, let's say for an uploaded video, the chunks were 0 to 3, 3 to 7, and 7 to 11. And let's say we're trying to transcode a TS segment for HLS from 5 to 10. We would not even read the first chunk. We just read the second and the third chunk. And so what did we do for transcoding? What kind of transcoding did we do before we let you tweet it out? Well, the answer is none. We didn't actually do any transcoding. So this allowed us to let you tweet it very quickly. But if we don't transcode, then how are we actually going to play the video when someone really wants to see the video? This is where the lazy transcode architecture comes in. So when we let you create the video, we also hydrate a bunch of virtual URLs that are kind of associated with that tweet, so the players see the paths. Like there's a HLS path, an MP4 path, or maybe multiple MP4 paths if you have different bit rates, and they choose which one they're going to play, and then they make an HTTP request. So and then that goes through a CDN, and our CDN origin, let's call it the video serving layer, is where the business rules are enforced. So the path actually has a lot of information about what variant is supposed to be transcoded. So the resolution, and also if it's a TS file, from what second to what second, and also anything about potential bitrate, etc. So that's all embedded in the file. And this video serving layer enforces the business rules, which variants are we actually allowed to serve. And like I said, it's the CDN origin, so it sets cache headers, etc. in the response. And also, it actually talks to the blob storage system before it fires up a transcoding request, in case we have transcoded this before, and maybe it fell out of the CDN cache and they came back to us, etc. But in the case where we're seeing this for the first time, so we need to go transcode it, it sends a request to the transcoding layer, which is actually consisting of two layers. So there's a coordinator layer, which is responsible for any kind of interaction with the blob storage system. And it does the demux and then the mux at the end. And it's responsible for breaking down the transcode work, but it doesn't do the transcoding itself. That's done by the transcode worker layer, which is in some sense kind of the dumbest layer in this architecture. It just does as told. It doesn't make decisions. And all the data, all the chunks come in through the request itself. And its response is the transcoded video. So it doesn't interact with any blob storage system. Here's a slightly different view of it in a diagram format. The one thing I haven't mentioned, I guess, is the metadata storage. So the CDN origin, when it receives a request for transcoding one of these variants, it looks up the metadata storage in terms of where are the chunks, how long is each chunk, so that it can do the math on exactly what transcode request it needs to generate. Otherwise, the coordinator kind of receives that request and then interacts with like I said, the worker layer, and then saves the responses to this. So the processing, the worker layer is never talking to the blob storage system. Everything comes in here. And this is a much bigger fleet than this one. I think our ratio is like 1 to 11. For every one coordinator node, we have about 10 to 11 worker nodes. In terms of being distributed systems and supporting failovers, etc. So what do we do? Twitter is in 2 data centers. We have one in Sacramento and one in Atlanta, and we are present in both DCs, and we have full failover support. If one of the DCs goes down, we can continue our operations in the other one, and we do DNS failovers and stuff. And we depend on our downstream services, the metadata storage and blob storage to actually provide replication services. So whenever we create a file or create metadata in one DC, we rely on them to replicate it to the other DC, so it's always available to us. And move the computation to the data. So what I mean here is when you do an upload, let's say you got affinitized to the Sacramento data center, so we have most of your, we have your bits there, but for some weird reason, or maybe a failover is happening, your last finalized call went to Atlanta. Well, we don't want to just try to, read all the bytes, across the US, right? So what we do is in that case, we look at that bit. If your file is actually in SMF1, we'll proxy it to our services on the SMF1 side, do the processing there, kind of relay the response, and call it a day. The nice thing about that is during a failover, it allows us to more gracefully kind of bleed traffic to the other side. So anything new that's being uploaded to the failed over DC will all stay there, but things that started uploading here but then got moved there, let's call it mid-tweet, we'll be able to move the computation. And deterministic transcode output. So one of the interesting artifacts of doing this lazy transcode is that when the CDM comes back to origin, the file isn't there. We need to generate the file. And we have multiple CDNs, so basically there's no guarantees that the CDN is going to call you only once. So every time the origin computes the video, essentially the file needs to be the same, because if we just keep giving different responses, that can cause all sorts of issues. So we had to tweak the way we use the libraries so that it always generates deterministic output. We had to play with things like multi-threading, disable, etc. So what are the benefits of this architecture I've explained so far? First of all, because we're not transcoding everything all the time, we are able to reduce costs a lot. We have a long tail of user-generated content that gets viewed very little, and it's very likely that some of the variants will just never be requested, and we never transcode those. So this helps us a lot on compute, storage, and egress costs. And a side effect of, again, this lazy transcode approach is that we're able to add new variants without worrying about backfill. As long as the new variant we're exposing is a smaller variant than the original you uploaded. Let's say you uploaded 720p and that's what we preserved as original chunks. And they say we have 720p and 480p now, but we want to add a 640p for just better, smoother transition. We can do that. That's no problem. And the way we do the distributed transcoding allows us to have a more even workload, especially at the worker layer where we do the bulk of the transcoding work, because we divide up our work to all same like 1 second to 2 second transcode units. And as long as you have a good load balancing algorithm, then you have an even workload on your most busy, most CPU bound layer. And with the way we chose to use the JNR wrapper on top of LSMASH and try to move most of the logic to Scala, we're able to leverage the high-level languages, and we had more engineers able to contribute to video logic without having to get their hands dirty with unmanaged code. Actually, I'm one of those people. I did things like a preview frame extraction, trying to decide which frame I want to extract, etc., without writing a single line of unmanaged code. So we launched that, and everything was great. And then what changed? So two things changed, and they're both related to duration. We had an acquisition of a company that was already able to do professional videos on Twitter, but not using the native stack. They had their own technology, and we wanted to eliminate, having duplicate text, transcode stacks. But they were already in their use case for professional publishers. They were allowing up to 10-minute videos. So for that reason, we needed to scale our platform so it can support 10-minute videos. And also on the kind of the existing native video support we had for regular consumers, not professional publishers, we wanted to also up the limit a little bit, and we went to 2 minutes and 20 seconds. I guess the max is the 10 minutes, so we had to scale to 10 minutes. And on the player side, unfortunately, we weren't able to retire support for MP4 files yet. Our mobile web player still required MP4 files, so we needed to be able to generate essentially a 10-minute MP4. So what are the implications of that? So distributed transcoding, we're still able to do it when we can, and we wanted to. That actually is faster, so we were able to retain the ability in V2. But media upload had to change because, first of all, we can't do the lazy transcoding of a 10-minute file on the lazy path, because lazy path actually implies somebody's trying to watch the video, and for that first person who has that CDN cache miss that's talking to origin for the first time, that transcode has to be really fast. So with the 30-second architecture, most of the time we're able to do that in 2 or 3 seconds, and our P99 is more on 5-6 seconds, but that's still short. There's no way we can do 10 minutes and 5 seconds. So we had to change the way we deal with the upload. Before upload, everything was fast, so we were able to do synchronously respond to the finalized call on the upload, saying yes, this video is good to go. But now we want to make sure that we can really transcode the MP4 variant. So we had to do that on the ingest path now. So that means on the V2 we had to deal with async uploads. Clients actually had to, and this includes API clients, they had to, after finalizing their upload, they had to keep polling to see when we're ready, and then we say, yes, it's complete and it's healthy, you can go ahead, or I encountered a problem, so you can't tweet this out. And lazy transcoding, we're still able to do it in the V2, but we can't do it for the, the long MP4s. And we switched to transcoding just like I said. And the other big problem with our existing architecture was the coordinator layer. The coordinator layer is kind of a bottleneck, especially in terms of I/O, right? Because everything, all the transcoded chunks came back to it, and it muxed everything and wrote that to the blob storage layer. So with a 10-minute MP4, that was just not good. It was going to be too slow, and it was just going to be I/O bottlenecked, potentially memory bottlenecked if there were a lot of videos being served by that node at the same time. So we had to implement something new. So we implemented distributed mux, which I'll kind of explain in the next slide. And similarly, our validation, when I mentioned we decode every frame, that was not yet fanned out, that was not distributed, that was happening in a single shot. So we had to change that as well so that we could do distributed pre-processing of the decoding of every frame. So this is the previous slide for V1 with slight modifications. First of all, we have now the Q processor. So in the V1 system, all the transcode requests were initiated by someone trying to actually watch a video coming via the CDNs. So now for the large videos, we have the Q processor directly talking to the coordinator, kind of pre-transcoding things. And now another difference is, so this guy was never talking to the blob storage directly, right? But now it is. So the way it works is the video processing coordinator still gets a bunch of metadata, decides how to fan out the work for a transcode. But now instead of sending the chunks, it's just sending information about what needs to be transcoded. And the worker layer is able to read the chunks directly, and then does this business, has a transcode output, and it does not return the transcode output to the coordinator. It actually writes it directly to the blob storage layer. And here we're leveraging what we call chunked writes, which allows you to essentially write the same file, but with just kind of chunk indices, similar to what we would be doing for the chunked uploads. And so the idea is, let's say you have a 35-second video, and you have chunks 1 through 35, like a request for each, and they're all writing with the same path to the blob storage, saying, this is chunk 1, this is chunk 2, etc. So then they all and they return some header information, like what are the samples, etc. What's the thing essentially that eventually needs to be muxed. So when all these guys are done, all 35 are done, the coordinator, what it does is it computes what the MP4 header should be. And we designed our transcode logic such that the entire header can go in the beginning. So then it writes chunk 0 to disk, and it finalizes file, and voila, we have a distributed write of an MP4 file. And we do something similar for validation. The coordinator layer kind of assigns responsibility. You look at seconds 0 through 1, you look at seconds 1 through 2, etc. And each one of those kind of validates that those ranges are fully decodable frames. So to sum up all the things I've discussed, for V1, our most important requirements were that we didn't have to deal with long videos. We were dealing with mostly short videos. And leveraging that fact, we wanted to make our platform as fast as possible in terms of letting you tweet a video, and also cheap and minimize costs. And so for that, we came up with the lazy and distributed transcoded, and then also for fast iterations, we wrote the Scholar app. And then for V2, the key change was that we had to support much longer videos, and this is where we introduced the async ingest so that we have more breathing room to do some transcoding up front. And then for scalability of how we transcode, we added the distributed mux and distributed decoding. Questions? Yes. So the question is, for the MP4 variant, people don't always watch the entire video, and do we do like just enough kind of transcoding to respond to requests, like kind of keep a connection open? So yeah, we don't do that. When we get it, because we're going through the CDN, we don't keep like a chunked kind of connection. So we just transcode the entire file.
Yeah, you measured any data to say how much over-encoding you do because of the bandwidth?
Yeah, we haven't measured that. Yeah. But it'll be very interesting for sure. Yeah. Or another option would be to try to eliminate the need for MP4s. Yeah. Right? Yes?
Which CDN do you use?
I'm sorry?
Which CDN do you use?
Oh, which CDN do we use? Today we use Edgecast and Fastly as our CDNs for video on demand.
Can you talk a little bit about what else matches?
Shiwei might also be able to help, but so the question is, can you talk a little bit more about LSMash? It's essentially another native kind of open source video processing library. And my understanding is it's got richer features for specifically MP4 containers. Yes.
So you're still using the V1 short?
Yeah, I mean, yeah, we still have well, I mean, V2 is kind of the evolution of V1. But yes, we still have lazy transcode, yes.
And when the lazy transcoders, because they've been commanded to, put usable emission blobs into the blob storage, that blob storage gets replicated to the other data center and stays there forever, so the lazy transcoders don't have to repeat work?
So first of all, the question is, does the file, the files we put in blob storage stay there forever? Not all the files stay forever. Only the original chunks stay forever. Everything else is a TTL, so that after a while, because one of the important things about Twitter is that something that's a month old almost never gets looked at. So we let things age out and try to minimize what we have to store. But we have to keep around the originals in case somebody comes back, and so that we can regenerate everything we need.
You guys adjust the quality based on end users' connection speed?
So the question is, do we adjust the quality based on the end user speed? Yes, we do. We do it especially in the adaptive streaming. So we let the players kind of take care of that. So the way HLS works is you have the master playlist, which is actually linked to a bunch of media playlists, and each media playlist is a different resolution and different bandwidth / bitrate. And based on their bandwidth conditions, players can change between segment boundaries to let's say if you're seeing connection issues and your bandwidth just dropped, you switch to a lower bitrate variant. And once things recover, you go back up to a higher variant. And usually that happens at segment boundaries, that switch. Yeah, so we do. That's and for the MP4, not so much. I mean, we have multiple options, and each client has its own logic for selecting, but it's up to the client. It's not, you can't adapt dynamically to mid playback with an MP4. Yes? What was the question? How are we better than YouTube? That's a very interesting question. What do you think, Josh?
I mean, I think, we would say like, why do video on Twitter versus YouTube? I think the big thing is for the reason that you do anything on Twitter is for the conversation. If you go to a YouTube comment section for any video, I mean, God bless you, you're gonna be a miserable person very quickly. That is not a happy place to have a conversation. Twitter, when people tweet, like we've even seen a lot of people tweet their YouTube videos, a lot of YouTube creators. So if you take like some of the YouTube stars who might have tens of millions of followers on YouTube, they will have more conversation on Twitter than they have on YouTube. So Twitter's really where the conversation is, and part of our goal is to like bring some of that video natively onto the Twitter platform. So I think that's the reason why tweet instead of using YouTube is for that conversational aspect and for the follow graph and sort of the nature of like the social aspect of Twitter that doesn't really exist on the YouTube platform.
Actually, I would also add one more thing to that. In my experience so far, YouTube is more geared towards, you have something in mind, you have a keyword, you're searching for something like how to cook spaghetti or how to fix drywall, and it's really good for those keywords, and there's just massive content. Whereas Twitter is a lot focused more on what's happening now, and based on your follow graph, you look at like what just happened in the last hour, and those are the things you watch. Yes, right. So unfortunately today but that was my initial topic, but I'm not able to talk about life, so my apologies.
Well, I mean, at a high level, if you're just asking from a product perspective, Twitter has 2 live products today around the video space. One is Periscope, which we acquired, actually I think before it launched, which lets you go live from your phone sort of instantaneously, similar to Facebook Live or YouTube Live enables. That is a totally separate stack today. We are very closely, literally in the same organization as my manager's manager is the CEO of Periscope, so we're closely engaged with them. And over the last year, there's been a lot of integration between the 2 products. If you do not have Periscope installed and do not have a Periscope account, you can run a Periscope from inside the Twitter app. So if you open the Twitter app, you say tweet, there's a button there that says go live, hit it, you're then doing a scope, and then that Periscope can actually get tweeted as a tweet, and you can watch it in your Twitter timeline. So we do support that sort of that's a user-generated live story. And then with the NFL last year, we launched our sort of premium live experience. We're running something like 200 hours a week of live events. Everything from, we run Major League Baseball games every Friday night. We have multiple daily shows we run with Bloomberg. We have a bunch of different live content that we're doing on the platform. And again, the focus there is really around the conversation around those things. It's not just being able to watch it, but while you watch it, you can see all the people who are tweeting about that video and the events surrounding that video, and you kind of can get involved in the conversation around that content.
Do you have a formal partnership with Bloomberg?
Yes. Yeah, Bloomberg, the question was, do you have a formal partnership with Bloomberg? Yes, they're a really great partner of ours. We have, like I said, we have I think 2 or 3 daily shows with them, and they're just they have a very large presence on Twitter. And they view it as a very important part of their sort of like their social media presence. Twitter is kind of a critical part of that for them, and especially given the nature of our vision is really, and Twitter's vision is really about live and what's happening right now, to the point that like when you go to tweet, the thing it says in that box is what's happening now, right? That's how we think of it, right? I guess it's just what's happening, but we think of it as what's happening right now, and that's a very big part of their business is like that kind of real time, totally current news. So.
Are the Snappy TV guys still part of the staff?
Yeah.
I have another mic, so there you go. Yeah, Snappy TV team is actually in the same organization as us. When you eventually tweet a Snappy TV video, in most cases that comes through our platform. There's a couple of exceptions that aren't worth getting into, but 99% of Snappy TV videos will go through the ingestion process that he just mentioned. Any other questions? One here.
How do you select which, what quality, what renditions you're going to produce? I mean, you can have a very wide variation in the bandwidth, a very wide variation in the.
I think the answer is the same as everybody else. We kind of go, okay, 2.5 megabit. No, I think there's a little more science behind it than that, but not that much more science behind it than that. I think experimentation is the answer. We have done a lot of work and are increasing our efforts around being able to experiment with different profiles in production and measure the way that they impact performance of various metrics that we care about.
Are you doing any quality aware streaming like Netflix, either to save bandwidth or optimize quality given that videos are so short?
Question was about quality aware streaming. When you say meaning like, maybe you can clarify, you mean like where the player knows how good they want the video to not look as good, or?
Yeah, like lower complexity scenes don't need to be encoded in high bitrate.
Oh, you're talking about sort of like variable bitrate or
It's simple.
more advanced variable bitrate. Not today, I don't think. Not exactly in the way that you're talking, I don't think, certainly. Looks like one more in the back, and we probably should finish up so the next talk can go. I can say that esport, like in terms of our live streaming product, we've run a number of esports events. We ran the Halo Championships a couple weeks ago. I think that was more popular than the Thursday Night Football games. Like it's an incredibly popular category. The largest non-Twitter owned client for our video upload service is the PlayStation 4 share feature for VOD clips. So yeah, there's definitely a big presence. Obviously there's a monster competitor in that space, which is Twitch, and I don't think we have. I wouldn't even say that we have the aspiration to compete with them directly in terms of like the scale of what they're doing. But yeah, we do have some capabilities in that space. There is some Periscope functionality that enables mobile gaming live streams through Periscope, which was actually built as part of like a Hack Week based here in the Seattle office. So we do have some efforts in that space, and like I said, esports in general has like a pretty good conversation going on Twitter, and some of the live video there has been very successful, so I would not be surprised if we see more of it. But content strategy is sort of like beyond what my team usually focuses on.
Thank you.
Thanks, guys. So Brightcove has an office here in Seattle, and the main thrust of that office is an analytics team. So Bryn and Ankur have graciously agreed to talk a bit about our analytics tools and the platform that they've been working on for at least a year, quite a while. That's launched recently, and Bryn looks very awake and ready to talk about it. So take it away.
Yeah. Hello, everybody. So my name is Bryn Waibel. I'm the architect. Mike. I'm the architect on Brightcove's video analytics team. I'm really just kind of starting it off for Ankur, who's going to get into the meat of the stuff, but we thought it would be useful to sort of frame the problem that we're trying to solve. So our primary concern is measuring, video playback, which, it doesn't sound like much, but it's difficult because, we have a wide array of viewing platforms, which is kind of the first part of what we're trying to solve, and it's hard to, among those different platforms, to create a consistent timeline, actually. And then one of the things that we really struggle with a lot is, we have high scale in terms of like number of sessions that we deal with, but really there's a huge variation in the number of use cases, and that creates a really difficult problem for analytics because you're kind of trying to solve every problem at once. So the viewing platforms that we support, we essentially have like 3 layers of implementations of analytics playback or analytics collection. We have a built-in HTML5 and Flash-based web player. It's a plugin to Video.js, which our company curates. And then for non-web, we have an iOS and Android SDK that works on Apple TV as well. And then any of the platforms that we don't have an SDK for, we have a data collection API that supports third-party implementations for measuring the playback. So the things that make measuring the playback sort of complicated in terms of use cases is, dealing with really short form, like the 10-second kind of stuff, 30-second kind of stuff, long form, live. The requirements for measuring that are just very different. The content lifecycle, so you have news, they have these like 300,000 video libraries that have like only 30 of them with any views in a recent time. Daily and episodic content that can last forever and continue to get views, and then the different revenue models, so advertising, subscription models, and then marketing, like looking for conversion kind of stuff. So sort of the first problem we had to solve, sorry guys, I just threw this together, is getting a consistent playback timeline for people. And so really the issue here is across the multiple platforms, being able to measure this. The OSs kind of provide different interfaces to what's playing back, and it really takes a lot of focus to get like an app to give you the same kind of information about a playback session that the web player will. So we started, I guess this is kind of the V1, V2 part. We started with just a distributed aggregation with no collation among our events. And what that means is we can count like views, we can say this part of the video was watched, we're sort of like just fanning out all these events and then aggregating them together into all these increment by one sort of sums. But we were really missing the ability to look at a playback session in the whole and say like, oh, this was a good playback session, this was a bad playback session, or say, that part of the video is getting rewatched really often. You couldn't tell that without collating. And the key there was that we were able to get these like full playback session metrics where we could start talking about scoring and classification and things that are really sort of telling us what's going on with individual users. Whereas before, we were just kind of talking about the data in aggregate. And Ankur's going to go more into it was really a huge platform transition to get there. Yeah, so I mean, basically, we get a whole bunch of events on distributed systems. We group these by sort of like different aggregations in time, and we have an API that gives you consistent access to them. And then on the back end, there's a whole lot of effort that we put into having the ability for teams among Brightcove to sort of look at and collate like discrete data so they can tell, like we'll measure the transcoding session and how that video gets out and all the playback events that occur for it, and all the, we collect all the bandwidth logs, and our teams are able to collate all that data together and look at a really complete picture of what's going on with their products. And so, there are sort of 4 mechanisms that they use for that. They schedule reports, which gives them COGS tracking, trend analysis. We have some monitors that are set up among that data to know when things are going wrong. We allow them to do totally ad hoc analysis in BigQuery. And we also do some sampling, and then we do larger cross joins and really discrete analysis of individual sessions that seem like outliers of some kind or that prove a concept for us. That is all I have. I'm going to hand it off to Ankur now. He's going to talk about the actual meat of the platform. Probably be more interesting.
So I'm Ankur Chauhan, and I'm a software engineer with the analytics team at Brightcove. And what we do is, well, before that, Brightcove is a company which has been there since 2004. So and continuously been working in the video space. So we know a thing or two about putting video on the internet, which apparently is a big thing. That said, there are lots of companies who want to put video out there, some of them others. So as you can see from this list, there are companies which put out content, which is like news, which needs to be out there right now. You need to measure how it's doing and take it off when it's not doing well. Or you have content which is like The Walking Dead. It comes out on every Sunday and gets a whole bunch of views, and then gets some views as the time goes on. And then there is Snapchat which disappears, but they have short form content, and so you need to be very fast with that kind of content and measure how they're performing, because people are not going to stick around. So just to give an idea of the scale, this amounts to about 8,500 years of video every month, about 7 billion events a day, which is basically beacon events telling you every possible thing that we can figure out from the player or from whatever means possible. And these all aggregate down into 80 million time series a day, and all of this is sort of maintained by it says five or six engineers. So really don't have time to do with ops and other stuff. So coming back to how we implemented this, so in the traditional way of making this kind of system, you have a Lambda architecture. At the top you see customers giving the events via HTTP to a thing that we call collector, which is basically a HTTP server which collects all the headers and parameters and everything that we collect into a streaming aggregation, which Bryn talked about earlier, and stores them into a real-time database. This part is lossy, as is Lambda architecture. And then at the same time, we log all these events to regular old-fashioned S3 old-fashioned files, which are essentially JSON logs, which we ship off to S3 and store them there, and have a Hadoop process which comes in and every day churns through all the logs and produces a reconciled view of the data, which is what we are sure of has happened throughout the day. And then at the end, there's an API which gets requests from a UI that we present to our customers, which want to figure out, hey, did my Walking Dead episode get all the views that I thought it should, and should I spend the $5 million producing it? And the API goes back to the database and aggregates both the reconciled view and the real-time, basically the streaming view of the data as it's coming in. So that's one part. And now comes the part when customer support comes to us and says, hey, stuff is not working. So we have had a Redshift database which allows for ad hoc queries over the entire set of entire set of logs and bandwidth log, which are from CDN, which are always 6 or 7 days late, and then our own logs and any other kind of things that we can put in there which would assist in diagnosing a problem or figuring out what should we be doing next to make the product better. So that's all fine, but of course we changed, we did some more work. And just to tell you why we needed to change was because apparently Brightcove is a very successful company, which is true. So we needed to scale it up. We needed to add more servers, and we are spending more and more time in just, expanding the scale of our service. On top of that, as Bryn pointed out, some of the answers cannot be answered if you're just looking at one event at a time. Some of the answers, like, did a person actually encounter an error while watching a video? Did they encounter an error before they press play or after they press play? Because they have different meanings. Because if you get an error while you were playing the video, you actually got interrupted while watching the video. But if you didn't press play and there was an error in buffering the video, prefetching the video, no one cares. So to answer those kind of questions, we needed to do session collation, which is for a given viewing session, you collect all the events together and you calculate some metrics on the whole thing. This means that you need some form of stateful computation. We can't just have one server sitting there and one server sitting there and getting half of the event here and half of the events there and doing their own thing. You need to sort of do a group by key. So, and as a result of that, you need a much more performant engine than what we had. So, we did our homework and we went out and we found that these were the things people were mostly recommending. Kafka, durable message queue, works very well, very performant, and it's a great product. There's a big community behind it. You can't really challenge that. Spark, lots of work has gone into it. There's, it's based on Scala, so it must be good because no one else can read the code. There's Hadoop. There's Hadoop, which again has been battle tested. It's pretty good. Cassandra, key value store based on on the original big table paper. The theory is good. The implementation is even better. And finally, Mesos. I like Mesos, and if you want to do anything at scale, you need to actually schedule work, and it was a thing which would let us move a little more easier rather than deploying on individual servers at a time. But even before we got ahead, while planning this out, there was already pages, and with a team of 5 or 6 engineers, if you have even one person who, even if there's one page, the pain is felt by everyone. So we are like, okay, all these systems, they're all new. We need to, first stand these systems up, get them operationally ready, figure out how to do production level traffic on this, and then keep them alive as they progress through time. Because we are on AWS, and AWS means that your instances will go away sooner or later, or you would need to recycle or at least do a restart of the machines. And if you don't know how to tune the 15 variables on Spark, you're going to run into problems. So we just didn't want to do that. It was a lot of work, and work which does not lead to features. So we went back to the drawing board. We thought about our problem. We sort of boiled it down to this. Events come in through the top. They get parsed by the collector. The collector basically says, this is the list of parameters that I got on the HTTP request. This is the list of headers that I got on it.
let me do some geo lookup, let me figure out which device it's running on, all that kind of stuff, and put it onto a message queue. And we do some computation and we put it into a database that we can query. At the same time, we want to put it in a data warehouse because we want to allow some kind of ad hoc analysis so that we can answer questions which come on from time to time as a part of running a service. Someone asks, why did this thing X take 10 times the bandwidth it used to do? So this was the main idea. So we went around and everyone claims the moon, and you go to AWS and they say, oh yeah, we have this amazing new product which is coming out and we'll solve every single problem under the sun. You go to Google and they say, yes, we'll solve every single problem under the sun. And if you go to EMC, they'll probably have one, and Oracle will just ask for something else. So, as every engineer is told in the first class of CS 101, I guess, trust but verify. You don't want to take any marketing material on its, on the face of it. So we went down this path. Let's do an incremental approach. Let's figure out what each part is, swap it out in its, in isolation, see if it works, see if it actually delivers the promise that it says it does. So this is the road to. So first of all, we went with the services that we own, the collector and the API. These are fairly simple-ish services. They encapsulate all the business logic, which is to do with how to query data sets, how to figure out events, and all those things. So we actually made a move early on that Kubernetes might be a very good solution. Because we had a managed solution available to us as provided by Google, as Google Compute Engine. So we said, Google Container Engine. So let's go the Kubernetes route, put them in Docker containers so that we don't have to worry about it. And the migration path is simple, well understood, well documented, and again, has a lot of support. And we don't have to manage a cluster, so yay. So we put that in. All of that went well. Next step is Kafka. So we looked around and we found that Google Cloud PubSub was a good replacement. It it's a globally available service, which means that we don't have to. So running a Kafka server, a Kafka cluster means that you have to run a Zookeeper cluster. A Zookeeper cluster dwindles around all the time and then will go belly up once in a while. And we can't have that. Plus, we don't know how to operate a Zookeeper cluster. On top of that, it would be another thing that we would have to maintain. And after maintaining Mongo, none of us want to maintain any other system ever. So we said, let's figure out a PubSub, and we went with that. So the things which PubSub give us is a globally distributed service, so we don't have to maintain mirroring of services in case of a data center outage or Zookeeper or anything like that. We can put in a unique message ID for each of our messages so that in case of retries, we can actually say, this message was already processed. We don't need to reprocess this message in case of a retry, and we resend the messages. Plus, given these two things, you can pretty much say that the possibility of loss of messages on the way to aggregation is pretty low. And we actually want to build on these metrics, on some of these metrics. So you can't just say best effort and call it a day. So we chose PubSub for that, and worked out very well for us. Next was Cassandra. Again, Cassandra, very good service. We don't know how to maintain it. We can learn. We don't want to spend all that time learning. We would much rather spend that time making features. at about the same time, which was about a year ago or maybe a year and a half ago, Google's Bigtable service, which is basically the implementation of the Bigtable paper out to the public and fronted by HBase API, allowed us to basically have the same data model as we would have had in Cassandra available as a managed service. That is not to say that you can't do that with Cassandra, but we found that this was a zero effort thing for us. It's completely managed, and you can toggle a few buttons and it scales up, toggle a few buttons and it scales down. And it was very reliable and performant. And we did our tests. We loaded up, I think, a couple of terabytes of data as fast as we could, and it worked just fine. So instead of spinning up our own Cassandra cluster and maintaining that, we went with Bigtable. Finally, ad hoc analysis. Before any of this came around, whenever customer support would come to us saying that, so-and-so customer is complaining that their bill is too high, prove that this is actually true. Why is their bill 3 times the amount that it used to be? It used to involve, Bryn going to his machine and downloading, for 3 days continuously, all the logs, and then writing this arcane grep followed by awk and God knows what. But if you're in the space of actually debugging problems, you'd know that Presto or Redshift or all these things which make the problem of loading up a whole bunch of data and then churning through it and giving you instant gratification in terms of a SQL statement is just amazing. So we looked around, and BigQuery was by far the leader in the whole space, and they had the ability to ingest our JSON parsed files directly. So we went with that, and we found that the thing that we used to spend a week just downloading data from S3, all the possible logs in the world, got reduced to 5 minutes of actual querying time, plus maybe a few hours of figuring out what exactly do we want to ask, what questions do we want to ask, and it was much more interactive. So in the whole theme of going with managed services, we chose BigQuery as the thing, as the workhorse here. So load all the files in BigQuery, and all of a sudden you have full query capability across all your data sets, which is a big win. And Rado can answer lots of questions about it. Okay, so all of that's done, but the biggest beast in the middle is Spark. Spark is big. Spark is complex because it has a lot of things to tune, which is fine, which gives you very fine-grained control, but it's another one of those things which we haven't tackled, and it was just a big pain point. So we looked around, and just about at this time, Google had published the data flow paper at VLDB, and about a year after that, they came out with this beta of Google Cloud Data Flow, which now has become an open source project called Beam. And what it does is that it gives you a unified view of your computations. One of the promises of Spark, which it sort of gave way to, was a unified way of expressing your aggregation and aggregation logic, so that it works the same way as it was working on batch data sets as well as streaming data sets, but sort of didn't get it right. Beam introduces the idea of processing time and event time, which actually brings together a unified approach towards batch and streaming, which means that whole thing about Lambda model having a streaming flow and a batch processing part just gets merged into one, and it means that you no longer have to maintain two different code bases. And because this is all decoupled, and because Beam sort of puts an abstraction on top of that, they can do the underlying runner, as it's called in Beam terminology, can put its own set of optimizations on your code. So it can figure out that all these pieces of computation can all be smushed into one function composition. So it won't do map A to B to C to D and write stuff to disk in between each of these processes, but rather directly go from A of B of C of D as a function composition. On top of that, it provided streaming reconciliation. We wanted to do session collation, and that was one of the things which was given out of the box. So we didn't have to implement that on our own. And when I say batteries included, I mean batteries included in the Python way, as in there are a million things that you can read from, and many more things that you can write to. So we wanted to read from PubSub and write to Bigtable, or read from PubSub, or read from S3 or some kind of blob store and write to a different service. And all that is something that's built into it, and it does the sharding of your computation out and then automatically rebalancing based on, oh, I think I can do faster here, or I think this needs to be scaled down. So it keeps our costs in check. So given all that talk, this is what we ended up with. And everything in that dotted box is a managed service, which means all that work, which would have been something like 1.5 years of just getting ready with operational stuff and learning things, and which can go towards actual feature development, which can go towards stuff that we haven't done. So we got a lot of time back from that, and what we did with that is, more API services, more kinds of aggregations that we can build, more BI tools. So if someone wants to say, let me validate if this idea actually works, they can go to the data rather than taking a swag at it. And so we got the opportunity to build a lot of BI tools and exposing more and more data towards our customers and figuring out how we can do this, do the session collation part of it. Okay, this is the nice one. Throughout this whole process, we learned a lot of lessons. The first one was, all the stuff that you learn in Hadoop land and with, just running systems at scale doesn't just go out of the window. We wanted to keep that. So first order of business is, if you want to get fast, don't do a lot of I/O. If you don't write to disk, and if you compute stuff properly, you will gain a lot. So reduce the amount of I/O. So if you can push the predicates all the way back to the source, that's a good thing. Use SSDs. SSDs are really fast. They're also very cheap nowadays. So using that instantly gains a lot of performance. Right-sizing Bigtable cluster can be said about right-size your Cassandra cluster, right-size your Edge-based cluster, which means that based on your write volume, you want to correctly size how much nodes you have, how much throughput are you able to accept. If you're writing at 100,000 QPS and you have allocated capacity for 10,000, you'll be slow. You'll be disappointed. So right-sizing that was a good decision. Second was using protobufs, or If you're Avro inclined, use Avro. The basic idea here is JSON is really good to start off, but it is very inefficient. A lot of time is spent just serializing and deserializing, serializing and deserializing. Whereas if you use protobuf or Avro, it gives you a schema to work with, which is like a contract that you can give to other teams and say, if you fit this schema, we will process your data correctly. And if you don't fit the schema, you'll know about it, and we can work on that. So protobuf, in our case, allowed us to get rid of most of the dirty data that we were getting. And most of the time, the dirty data comes mostly because people forget to put in the magic field that you need them to put. Backward compatibility is free. If you add a field, it takes the default value if it doesn't exist in the input. And if it does exist, it takes the new value. And it's a binary format, so it's optimized. It's very compact, and machines deal with that kind of stuff very well. Yes?
Did you push protocol all the way to the client level?
Not to the client level. The client still talk just HTTP gets, but right at the very top, as soon as we receive that, we convert it to protobuf. So as far as we could push it up, I'm sure we can push it up even further, but yeah. And then finally, because analytics, you monitor everything. You want to, we made a whole bunch of dashboards, and each of those systems, they have their own dashboards to figure out what part is going wrong, if we can improve some part, and I'll show you one of those dashboards later. And we also believe that alerts are a better thing, and just giving someone just blank numbers is not useful. In our case, an alert should be actionable. That means if you say CPU is over 85% means nothing. But if you say that, all of a sudden that your backlog of messages on PubSub is 7 hours long, you immediately know that you're not processing fast enough. It doesn't matter that your CPU is churning at 100%. It matters that you're not able to keep up with data. So the thing to take away here is build metrics and build alerts which are actually actionable for your use case. And finally, in our case, the Dataflow team at Google was really helpful in figuring out our bottlenecks. And yeah. Okay. So all that done, where did we end up? So right now we are working towards making adaptive aggregates, which is a fancier way of saying we have a thing which watches our query, the kinds of queries that we get. We collect the queries for a set amount of time, and we figure out what materialized views we need to keep. That way we can pre-aggregate data and answer the queries better. So all of a sudden we see people querying for, I don't know, like device by country. And we don't have a pre-aggregated answer to that. Our system will, over time learn that, if we had this aggregate, we could answer it in 6 milliseconds versus right now it's taking 10 seconds to answer that. So over time, it adapts to the query pattern. More BI tools is always better. You can answer better, you can answer more and more complex questions. You can figure out what's going wrong where and get to the bottom of it faster. And finally, unify analytics and billing pipelines. Historically, analytics is, you collect data one way and you present it one way, but the billing part of the system sort of interprets the same data from the point of view of how a contract is built. And this is, this may lead to cases wherein it doesn't always exactly match. So but because we have exactly once delivery and of our messages, and it's acknowledged all the way from end to end, we can say that if we received a message and we acknowledged it, we will process it, and we'll process it exactly once. So, which gives us a very high level of confidence that we won't double count something, or we won't undercount. We may undercount it within a threshold, but we won't undercount it by a lot, which makes two big code bases become one and have a consistent answer. And yeah, all of this would have been 1.5 years away had we gone on to building our own stuff. Okay. Demo cheating. Okay. So this is, I'll pause. So this is how, yes, American Dictionary. Okay, so this is how our production pipeline looks like. So, events come in from the top from different sources, and they undergo all different kinds of computation, snappy decompress, break them out into individual events, and then finally write it to the database. The neat thing here is that each of these boxes directly correlate with pieces of code. They are classes by the same name. So when you click on any one of these, it tells you how much time is being spent. So like 10 hours of compute time was spent in just that piece. So if you all of a sudden ship out a change and you see that this one part which used to take 5 days per day of compute time, all of a sudden started taking a huge amount of time, you could point out exactly which class got altered, and it gives you direct correlation between what's actually running and how it's coded up. What that lets you do is that the runner can have a completely different set of optimizations than what you need to do. So if you're from the Hadoop world, sooner or later you're going to end up doing some kind of somersaults to get the right amount of performance. You'll either do a a map side join, or a combiner, or some asinine thing like that. But but with the beam model, because that is kept at a step away from it, in this case, for example, everything till like here is fused together as a single function and gets computed just once. That means all those individual classes, you can code them up what makes sense to you. Like you can break them up into 15 functions, and the optimizer will figure out that, oh, this function can be pipelined with this function, and this function's output can be pipelined with that function, and this functions can be with that function. And if you want to get more details on it, there's a paper called Java Flume, which details about exact optimizations, but it's kept away from you, and you can let the runtime deal with it. And then the nice dashboard that we created to actually run this is this. First of all, black, which means that when you're sleeping at night, it won't worry you. Okay, so the things that to keep in mind, every line here is directly pointing towards either a place to pay attention to, or a place where you need to go towards to find the answer on a particular page. So if a page says, your PubSub backlog is 7 hours old, you just look at the first line and you say, okay, yes, it is 7 hours old and we are not keeping up. Or yes, it's 7 hours old and this is when it started. The second line, which means that it's an actionable metric, that something changed either on our ingest side or the pipeline just fell over. Same way, upside down. Same way with the second line, which sort of gives you an idea of how each of the workers are doing. So the CPU in our case, it may not be in your pipeline, but in our case, it tells us that the CPU usage, if it goes to 0, probably means that your workers are not doing anything because you are not processing anything, which most of the time means that something really catastrophic happened, like you ran out of disk space and you need to have bigger disks. And if you see the sudden drop, it's right at the hour boundary. We do hourly aggregations, so you build up state till the end of the hour, and all of a sudden you flush all that state, so it goes down. And you build up state and flush that, so it gives us a high-level view that our service is doing better, is doing well. And the dotted line over there is sort of our, keep calm line, that you want to keep the processors as utilized as possible, but you don't want to take them to 100%, because whenever you take things to 100%, distributed systems frown upon that and they just start behaving weird. So you want to keep it high, and 85% was what we were recommended as a good threshold line. So yeah, dashboards will help you a lot. And that's it that I have. Any questions on, yeah?
I have two questions. One, before the managed services, did you consider Storm instead of Spark, and if you did, why did you choose that over? And second, do you provide your analytics services only to those that are using your transcoding, or do you also have your own transcoding and you just provide the analytics services?
I'll answer in the reverse order. Do we offer analytics? The question is, do we offer analytics only to the folks who use our transcoding platform? And the answer to that is, if you can send us events, we will process them. Which means that you can, if someone was to transcode their own stuff and put it out on a CDN and integrate with our analytics collection API and all those things, their events would reach us. We would aggregate them, and we would, they would be just like any other. What was the first question again?
Storm versus Spark.
We did look at benchmarks that were conducted against the same thing: Storm versus Spark versus Flink versus Dataflow. Storm's throughput on Trident, I think, which allows for acknowledgements per message, was not high enough for our volume, and it would have been a bigger cluster that we would have had to maintain. Plus it does not have the concept of event time, which is kind of crucial if you want to do sessionized windows, because the thing that you want to say is there has been a gap of 10 minutes between the last event that you received. And without an event time, you can't particularly say that. That's not to say that Storm can't have it, it just doesn't. Yes?
So, question is, remember, you mentioned all these events are fired off the web-based player, actual web-based. Do you have any solution for mobile?
Yes. So, in cases of, web-based players use the JavaScript plugin. There's a mobile SDK for iOS and mobile SDK for Android, which does all the instrumentation at different points in the video playback. to give events when, at the correct times they occur. That said, none of them can measure properly, so yeah. Time does not flow front to back in the real world. It always goes backwards. So yeah. Anyone? Yes. End-to-end, like few tens of seconds, maybe. 8 to 10 seconds from. We do speculation. We do speculative updates to our database every 30 seconds, but our events are acknowledged to PubSub with a lag of about 3 to 9 seconds. So if we really wanted to cut down the lag between how soon it's available, we could cut it down to like, every second writes, but you don't need to go more than 30 seconds. No one's paying attention that much.
At the end of the hour, the latency from our front end to the database goes up by, you can see it in that chart actually, it goes up by like a minute and a half or sometimes up to 2 minutes. And we're working on that sort of hourly commit that we do for reconciliation. We're working on ways to even that out over the hour so it doesn't hit us so hard. That chart's interesting too. The one on the second from the top on the right, we're IO bound. We were IO bound at that time, so you can see like how the IO like spreads up at the beginning of the hour.
This
and
one.
It hits a throttling point. We realized we needed more storage. Google scales IO throughput with extra storage, and so we just increased the storage, and now we're not bound by that anymore.
So is the audience more internal utilization and billing, or is it some of this marketing front end Conviva style, developer debug,
Until about
layer issues or things of that nature?
until about maybe 6 months ago, the only people who were really looking at this data were our customers. So publishers that were creating videos, so like the Conviva style. This platform has really opened up the door for us to do a lot more internal BI, which is, we're kind of focusing on that a little bit more right now because it's, honestly, it makes it benefits our customers more, it improves the product better. Yeah.
Yes, tracking location data for the videos that you're tracking. So if you have a video out there, is it like you watch more in California or Indiana?
Yeah, we track. We use IP-based tracking with MaxMind is the tool we use, and we track location and network, ASN, ISP, that kind of information. And then we've just started kind of looking at CDN distribution too, which is a really interesting part of it.
You really target ads based on that.
Yeah, right now we don't do ad targeting from our platform because we work with other ad providers, but our server-side ad insertion guys are really hot on that, getting that data from us.
Yeah, all of this is used by both internal and external, and we're expanding our use on the internal side because, it lets us answer their questions a little more better than what they would always know how to answer themselves.
I just wanted to say we do not offer video analytics as a standalone service. I can't remember who asked that, but I mean, theoretically you could set it up, but it's not something that we offer as a standalone.
Oh yeah.
Is that it?
That's it.
Thanks, guys. I want to thank everyone for coming. I'm not sure when the next meetup will be. Hopefully we'll do one in May. I want want to thank Twitter for hosting us. This has been awesome and giving some great talks. And Ankur and Bryn for giving a great talk as well. Ankur did that similar talk at Google Next, which was cool to watch. So thanks, everybody. Have a good night.